Hello world, my name is Victor Engelmann. Welcome back to this video series about professional network design using Linux. So one of the first things we did in this series was we took our network and we divided it up into several virtual networks. And the idea behind that was that we want to protect devices from other devices. Okay, so that when one device might be infected with something, some malware, then that device should not be able to attack the other devices on the network. Okay, and yeah, that's what we decided to use VLANs for. So we divided the network up and put devices into different of these virtual networks so that only the devices within the same virtual network can communicate with each other. Now that of course is a problem because let's say you put your printer in a different network than your workstation, then you cannot print anymore, right? And that's why we've put a router into that network and put that router into all of the virtual networks. And yeah, that router would just forward all the packets that it would get, okay? And we set this router as the gateway for all the machines so that if they were trying to communicate with something outside of their own network, which is decided based on the network mask, then this packet would be sent to the router and the router would just forward it. And yeah, like that, everybody was able to communicate with everybody again. So this really made the whole subdivision into virtual networks almost pointless. The only difference at that point would be that broadcasts would stay within their own virtual network. So yeah, that basically removed all the protection that we had established before. And yeah, this is what we will address today. We will get this security back. Okay, so we still have this router and the router will forward the packets, but it will not forward all packets anymore. Okay, so we will run a firewall, a packet filtering firewall on the router, and through that packet filtering firewall we can then say, for example, machines from VLAN 4, the workstation VLAN, will not be allowed to communicate with the DHCP server on port 22 anymore, for example. So that the regular workstations cannot try to access the critical network infrastructure through SSH anymore, for example. Okay, and yeah, for that we will use the packet called iptables. There are other firewall programs, but most of them are more designed for endpoints. But yeah, iptables is a bit more complicated, and I wouldn't recommend using it on endpoint devices. But yeah, I think for routing, iptables just fits the task for routing more. Okay, so let's connect to the router. Okay. And now I will install the packet iptables. Okay, it's already installed. So let's talk about iptables. Iptables, as the name suggests, comes with several tables containing IPs or IP ranges, to be more precise. And whenever you have a packet, or in several situations, when you get a packet, when you try to send a packet, when you are supposed to forward a packet like a router does, then iptables takes that packet and compares it to its tables. Okay, and that's really important to understand. It will start at the top of the table and go down from there. And when it finds a rule that matches the packet, then the decision for that rule to accept the packet, to reject it, or to drop it will then be the thing that iptables does. And at that point, it stops comparing it to other rules further down. Okay, so that's important. The first rule that matches is the one that will be used. And that, for example, means that you should always make your rules to have first the more specific rules and then the more general rules. Because if you have a more general rule before a more specific rule, then that more general rule will overrule that more specific rule, then that more specific rule will never match. Okay, so how do you do that now? Well, with the program iptables, you control everything iptables does. Okay, so for example, with -L, you can list your tables. For example, let's list the input table. Okay, there's nothing in there. The output table is also empty. Yeah, we haven't put anything in there yet, so it makes sense that these are empty. And it already says here that there is a policy, and the policy is in both cases here accept. So the policy is really the default rule at the end of the table. Okay, if no rule from your table has matched, then this policy will be applied. Okay, and we can change that policy by calling iptables -P for policy of the input chain and set it to reject incoming packets by default. But that would be a very bad idea if I hit return at this point, because then it would, since we don't have any other rules that would allow any packets, this would mean that I would just not accept any packets, and then I would lose access to the machine completely. Okay, the machine would be bricked effectively. I mean, you can pull the SD card out of the device and attach it to a different machine and edit the IP table there manually, but unless we save the table, it will be gone at the next restart anyway. So if I had pressed return at that point, I would only have to restart the device and then I could access it again. And that is already a good question. If the tables are not persistent, then how do you save them? You can do that with iptables-save, but this will only print the tables to standard out. Okay, that's really important. Right now the table is empty, that's why I have no output here, but if I really want to put that into a file, then I need to manually redirect that to something like etc iptables rules.v4 for IPv4. Okay, and then if I want to restore the rules, then I can restore them with iptables-restore from that file. Okay, and you will find a lot of websites advising you how to put these two commands into your startup scripts, but that's not really user-friendly. What you can do instead is you can install the package iptables persistent. Okay, I can save the rules, but it's pointless because there are no rules in there. Okay, but this message told us it only loads these rules at system startup. Okay, it doesn't save them when you do a clean shutdown or something. So you still have to run iptables save and put that into that file etc iptables rules v4. You still have to do that manually to save the current rules. Yeah, I don't think that's very user-friendly, but on the other hand, that protects you from accidentally bricking your device. So if you lose connection to your device, you just restart it. It hasn't saved the rules, and then you're back to a state where you had access. Okay, so let's start putting something in these tables. Okay, and for starters, I want to create a rule that forbids machines from VLAN 4, the workstation VLAN, to connect to anything in the VLAN 2, the server VLAN, on port 22. So I want to forbid SSH connections from regular workstations to the servers. iptables -A to append something. What do we append this to? To the forward table. Again, we have the typical tables: input, output, and forward. Input is for packets that are directed to yourself, but this is on the router, and we are talking about packets that are going through the router to the DHCP server, right? Okay, then we can set the source address to 10.1.4.0/24. So anything coming from VLAN 4. With -d, we set the destination 10.1.2.0/24. So anything coming from VLAN 4 to going to VLAN 2. We want to reject with -j. We specify the decision that we want to make for it. With -j accept, we would accept the packet. With reject, we reject the packet. But we could also say drop. Okay, drop and reject are very similar. They both don't accept the packet. But the difference is that if you drop the packet, you just ignore it. When you reject the packet, then you send an information back to the sender saying you're not connecting. Okay, I'm not allowing this. And it's using a TCP reset packet for that. Which, yeah, we've talked about reset packets in the video about TCP. But that might be an information that you don't want to send out, right? If we are talking about packets that come in from the open internet, you would rather drop this packet and not send some information back that tells some attacker about your infrastructure. Like, yeah, this machine exists, you are just not getting a connection on that port, right? That's still an information that an attacker might be interested in if he sees, okay, this machine still exists, and then he might try to attack that machine on a different port or whatever. But when you just drop it, you pretend that the machine isn't even there. Okay, that's the difference. Okay, like this, we would reject anything coming from VLAN 4 going to VLAN 2, but we only want to forbid SSH connections. So we would want to filter port 22, but yeah, not every IP packet that you get even has a port, right? So you need to first check if the packet you're getting even is a TCP packet, and only then you can look at the port and see, okay, this is a TCP packet on port 22. So you would set the protocol to TCP and match against TCP. This -m is something that you often see when you have these sub-options. You see here you have two dashes. Options with two dashes are sub-options for these matching options here. Okay, and dport is a sub-option of this TCP handler. Let's open another connection and test if this actually doesn't work now. Let's try to connect to 10.1.2.100. Connect to host, connection refused. And this is what I mean. You immediately see that the connection was refused because you have gotten a packet back that told you no, I refuse this connection. Okay. If you had dropped it instead, then this call would have waited for a timeout. I mean, we can do that. Let's flush the forward table. Okay, I've just removed everything from the forward table again. Now I can connect, but that's not what I want to do. So now let's set this to drop instead. And you see now you don't get this connection refused. Now it's waiting for a response, but it doesn't get a response, and eventually it will time out. And yeah, that's the difference between reject and drop. Generally, I would make my table such that you reject packets when they come from within your company and drop them when they come from the outside. Okay. We have built our network such that the VLANs correspond to the interfaces of the netcore, right? We always have these ETH0.2, 3, and 4, which are members of the respective VLANs, VLAN 2, 3, and 4. And because we have done it like this, we could also do it like this. If a packet is incoming from interface ETH0.4 and should go to interface ETH0.2, then we do that. I'm not sure if that would have a better performance or not. I just wanted to mention it, that you can also limit things based on the interfaces that the packets are coming from and going to. And yeah, as I said, this might make sense depending how you want to do this. Okay, the next thing I want to talk about are pings. Right now, our default rule is to accept packets, right? So this means that if we want to suppress pings, we would have to make a rule that says pings are forbidden. I personally like pings. I think they are really useful, and I personally wouldn't suppress them, but there's a lot of people who say that when you allow pings, then a machine could be flooded with ping requests, and yeah, that's of course true, but again, I personally still think that they are too useful to suppress them. But either way, even if you want to allow pings, if we set the default action to reject or to drop packets, then you have to make an explicit rule to allow pings. Okay, so either way you want to have it, we need to talk about pings. Okay, so iptables, append a rule to the forward chain. Let's say again from VLAN 4. To VLAN 2. And we will reject these packets. Okay, now a ping, as we've discussed in the video about the anatomy of network packets, a ping is not something going through TCP or UDP. It doesn't have a port, so you cannot say, hey, I want to block this port. Okay, this is a different protocol. So we need to compare this against the protocol ICMP. Okay, and with -- ICMP type, we can then select 0 for ping replies and 8 for ping requests. Or we could just say anything going on the ICMP protocol is disallowed. Instead of 0 and 8, which are really technical informations, we could just say echo request. So instead of an 8, which is really requires deep down knowledge about ICMP to know that an echo request is a number 8, instead we can just use this name echo request instead. Okay. So like this, we disallow the requests, right? So now I shouldn't be able to ping 10.1.2.100. Yeah, destination port unreachable. But this only blocks echo requests going in one direction, right? If I connect to the DHCP server now, I should still be able to ping my laptop here. It's 10.1.4.21. But it doesn't allow us to connect. So if we want to connect to it, we can still use the router as a jump host. I mean, we might want to block packets coming from VLAN 4 on the input chain, so that the router would also not allow SSH connections from VLAN 4. Okay, but anyhow, right now I'm still allowed to connect to the router on port 22, so I still am connected to that, and from here I can still connect to 10.1.2.100, and from here 10.1.4.21 I can still ping in the other direction. This is something that is a bit surprising if you ask me. I mean, normally connectivity is something transitive, right? If I can ping the router and the router can ping the DHCP server, then normally, under normal circumstances, you should also be able to ping the DHCP server, but it's not the case, and it's not even symmetric at this point. From the laptop I cannot ping the DHCP server, but the DHCP server can ping the laptop. Okay, now so far we have worked with a table that had a default policy of accept, right? So everything that we wanted to disallow we had to explicitly disallow, and everything else would be allowed by default. Now that's really not a good idea, especially not in these zero trust times where we really want to reduce everything to the absolute bare minimum of things that you are allowed to do. And yeah, such a default allow policy is not a good idea in such a situation. So what you want to do instead is you want to set the default rule, the default policy to reject or even drop, and really only explicitly allows things that you want to be allowed. Okay, so let's flush the table again. Okay, so let's configure our table to drop packets by default. At this point we cannot set reject because yeah, IP packets don't necessarily are TCP packets, and if you have some protocol apart from TCP, you cannot reject it in that sense, right? Because if you have some different protocol that doesn't have these reset packets, then IP tables wouldn't know how to reject a packet. So we cannot set this to reject, right? Bad policy name. So we have it on drop. Now at this point, my laptop has lost its internet connectivity because its internet traffic is also going through the router. So if I would now run something like curl Google or something. I don't have curl installed. Anyhow, if I open a web browser now and try to go to google.com, for example, this is also blocked, or dropped to be more precise. So so now I really have to allow list everything. I have to explicitly tell IP tables what traffic you want to allow. So something from let's allow our entire network without specifying the destination. Yeah, maybe I should tell it what to do with that rule. Append it to the forward table. Okay, and also for port 443, which is HTTPS. Okay, let's try again. Okay, now it's trying to go to Google. I should have sent the request out, but the problem at this point is that the response is not allowed to go through. Okay, and yeah, this is really a very, very important rule that we will talk about now. You absolutely need a rule that keeps track of your connections and allows answers to established connections. You do that with IP tables, forward, on the forward table, with -m, contract for connection tracking, --ct as contract, state, established or related. Okay, so This is a quite general rule. We haven't specified any source or destination IP range or port or anything. But yeah, this now, this rule is there to keep track of your connections. And it says, if I have allowed this machine to connect to that machine, then I will also allow anything coming back from that machine going to this machine, as long as it's on the same connection, as long as the ports match the tables of this contract module, where it keeps track of the ports that are used in the different connections. Okay, so let's try again. Google.com. It still doesn't work. I think I know what the problem is. I'm trying to access Google.com, right? But before I can access that, I need to know an IP address for that, and I need to resolve the host name for that, which means that my laptop needs to send a DNS request to the DHCP server, which also runs the DNS server. And that is also suppressed by the router at this point. So let's see if anyone from inside my network tries to access 10.1.2.100 on protocol. DNS uses UDP. And it goes through port 53. Okay. So now I should be able to resolve it, but at this point I should be able to connect to the DNS server, but now the DNS server cannot connect to the other DNS servers to get upstream information. So if 10.1.2.100 wants to connect I'll just allow any other IP address for DNS. So I mean, we could limit this to 192.168.178.1, my Fritzbox, and then make another rule for 8888, for example. But I think that would effectively become rather paranoid. Let's try it again now. Now I can access Google. That really shows you how difficult this whole business can be. When you really want security and you go with allow listing approaches, then you really have to explicitly allow everything that you want to allow, right? And that really requires you to know what you want to allow, right? So what ports are allowed, what protocols they use. Right here, DNS going over UDP, that's something that you need to know for that. A nice side effect of this, by the way, I'm running my own DNS server, right? And I can block domain names through that DNS server. But let's say you have a coworker who might have some access rights on his machine and wants to circumvent this domain block by using some other DNS server like 8888, for example. Then yeah, if they tried to query that domain name from another server, that goes through port 53. And yeah, port 53 is blocked for everything except machines being allowed to query our own DNS server here. The DNS server itself is the only machine that is allowed to communicate on port 53 to outside machines. So that effectively really forbids that anybody can circumvent that restriction. Okay, the next thing I want to talk about is network address translation, or NAT. Yeah, network address translation is generally frowned upon because under ideal circumstances you should never need network address translation, or NAT. So whenever you use network address translation, it's really just a sign of something else being misconfigured in your network. But yeah, the reality is that, well, networks aren't always perfectly configured, and also there are situations like, for example, you can have industrial machines which don't have a really good network stack in some cases. But generally, network address translation is only needed when you have two machines in different networks and you want them to be able to communicate with each other. And yeah, one of these machines has a route to the other through some router, of course, but the destination of the connection doesn't have a route back. Okay, that's really the only situation where you need network address translation, because what that does is the router will pretend to be the origin of the connection. Okay, so that the recipient of the connection then thinks it's talking to the router, and it has a route to that router because, well, the router is in the same network, so that packet can stay within that network, and then the router will take the responses and rewrite them and send them back to the actual origin of the connection. And for that it has to keep track which connection came from which device. Okay, that just eats up some system resources, and it's not ideal, right? In the ideal situation, just both machines should have routes to each other, and then you wouldn't need network address translation, with one exception. If your network is behind one, if your entire network is behind one router which has internet access, right, and this has only one external IP, then yeah, your internet connections for all the other devices would be netted, network address translated, because well, when you send something out to the internet, it goes to your router, and then your router translates that packet, sends it to some server, let's say google.com, and the response goes back, of course, to the router, because if that is your only public IP address, then you have to put that into the packet so that Google will send the response back to you, and then you can do your network address translation. And but that's also only a problem in IPv4 networks. In IPv6 things have changed very much, and in IPv6 every machine has its own public globally routable IP address, so Google would actually get that public IP address of the of your machine, and where the route for that IPv6 packet just goes through your router. Okay, then your router has to route that forward to your actual machine. But yeah, that's, I don't want to go too deep into IPv6 here. So yeah, let's see how we can do network address translation. And for this I have prepared a little PHP script. Okay, so you see this is running on a little web server in my network, which just tells you your IP address, right? And yeah, you see I can send data to that server because my routing is set up properly. But if we now assume that this web server doesn't have a root back, I mean, I could remove the root on that server, but I would just set up the network address translation, even though the server could send answers back to me. Okay. Good. You do that also with IP tables. You do that in the post-routing phase, because the laptop sends the packet to the router, right? And the router should look into the packet in the forwarding phase, right? And make decisions based on, hey, is my laptop even allowed to send that? Okay. And the post-routing means only after it has done these checks. After that, it can change the sender address, because otherwise it might get confused, right? If it first changed the sender IP and then would check, hey, is this packet allowed to be sent to the web server? Then it might say, hey, I'm allowed to send something to the web server, and this is coming from me, therefore I'm allowed to send that. Okay. Now this has to go to the network address table. And let's say if anything comes from 10.140/24 and goes to 192.168.178.31, then the decision is to masquerade the packet. Okay. Now let's see what happens if I now ask the same question again. Yeah, now you see this is the IP address that my router has in my VLAN 1, right? So, so you see now the web server thinks that the packet came from the router. I want to mention one more thing. If we were talking about packets going out to the public internet, then your destination might be something like 10.0.0.0/8, but you actually want the opposite of that, right? If something is supposed to go out to the internet, then that's the opposite of the packet staying inside your own network. You can do the opposite just with an exclamation point. Okay, so destination is not in the 10 range. Okay, so if the destination is not in the 10 range, then I masquerade it and route it wherever it's going. Okay, and that also works for other things like the protocol TCP. You can put exclamation point in front of that and say everything except TCP. Okay, that was masquerading. Now let's talk about port forwarding. Port forwarding is very similar to network address translation because it also rewrites the source and destination IP addresses of the packets, but kind of in the opposite way. You know, we just had the situation that my laptop has a route to the web server, but the web server doesn't have a route back. And yeah, with port forwarding, it's kind of the opposite. Like you could do that when the laptop does not have a route to the server, but maybe the server has a route back. but the server shouldn't route packets back directly anyhow. The thing what we are doing then is we can tell the router to pretend to be the web server. Okay, so it will take packets on port 80 or 443 and will then change the recipient to the web server, and after that also masquerade it, so that the web server then also sends the responses back to the router. And okay, so how do we do that? We added the NAT table, network address translation. First, in the pre-routing phase, we check if it's a TCP connection. We check the port, let's say 8080, for example. And then our decision is to do destination network address translation --2 destination. So here we now set the new destination for the packet. So the router has gotten a packet from us. We are thinking that we are talking to the router, but the router takes a packet, changes the destination to 192.168.178.31, and also the port 80. You know, we can change the port. Here I had 8080 and we are changing it to 80. Okay. This has to be done in the pre-routing phase because we are kind of correcting the route here. Okay. So even though this packet was directed to the router, the router should handle it as if it had been directed to the web server in the first place. Okay, that's why we make this change in the pre-routing phase. And then we have to masquerade it just like we did before. So packets, TCP packets going to the web server on port 80 should be masqueraded in the post-routing phase, okay, just like we did here. It's just that we reroute the packet before we process it. Okay. Now let's see if we can access this script now through 10.1.4.254. Okay, it has refused to accept it. Yeah. Of course, I've forgotten to set the port to 8080, and now we are getting the response that we want. You see, now I can communicate with the router the way I communicated with the web server before, and yeah, from the web server's perspective, it looks like the connection is coming from the router because we are masquerading it. Okay, that was port forwarding. Now let's talk about user chains. But this is actually a very advanced topic that you probably never need. The idea of a user chain is, you know, so far we have always only used the tables forward, input, output, pre-routing and post-routing, right? But with a user chain you can make your own tables, and you can do that using iptables -N, and then you have to give it a name like foo, for example. And now you have another table that you can list and flush and add to, just like the others. You see now there's this chain now called foo, and yeah, you can put rules in there, but why would you even want to make your own chains? The thing is, let's say you have a lot of rules for all your VLANs, for example. Then you might want to put the rules for each VLAN into its own chain, and then in your actual forward chain you would only check which VLAN is this for, and then redirect the tests to that chain for that VLAN. Okay, so so let's say I make a chain for VLAN 4, okay, and then I might put something in there. Where I only test the destination, because I would only be in that chain after I've checked that the source is VLAN 4. So if I'm coming from here, then if the destination is in VLAN 2, SSH, then I might decide to reject it, right? So now I have one rule in that, but it would never be used right now. So if I want to use that, I have to put a rule into the forward chain in that case, which redirects everything coming from VLAN 4 to that chain. You can do that with sudo iptables add to the forward chain a rule that only tests the source for 10.1.4.0.24. Okay, everything that comes from VLAN 4 will be redirected with this J, the same that we usually used to reject or accept things. We now say that the decision is to go to the VLAN 4 chain. Okay, so if iptables now gets a packet from VLAN 4, it goes to this new chain, and there it would then see, hey, if this is sent to VLAN 2, then I will reject it in case it's for SSH, right? You can delete user chains with -X. Okay, now my chain foo that I had here is gone. And yeah, this is how you can use user chains. There is one other thing I want to point out. Here we have used JVLAN4, okay, which is similar to a function call in programming languages, in that if you have you are coming from this rule here, okay? If this rule applies, then I go to VLAN 4, okay? And if I do that with this J, then the rules after that will still be applied once this VLAN 4 chain is done processing, okay? So if you have any more rules after that, they will still apply. If you jump into this VLAN 4 table using -G, like goto, then yeah, it's similar to the goto from programming languages again, in that if you have rules after this goto, then the rules after that will not be processed after the processing of a VLAN 4 chain is done. Okay, so that's the difference. And but it's still the case if you have 3 chains, for example. You can jump into a second chain. Then from the second chain you can go to a third chain. This goto removes the second chain from the stack, but the first chain is still there. So if the third chain is then done, then it doesn't return to the second chain, it returns to the first chain. Okay, so yeah, anyhow, this is really advanced stuff that you probably never need unless you are doing something like global routing when you're working at an ISP, where you might have something like a binary search for the target IP range or something like that. Yeah, again, I think this is relatively complicated and doesn't improve the performance under normal circumstances that much. But yeah, that's all I wanted to show you today. But always keep in mind, really remember this, iptables goes through these tables from the first to the last, and the first one that matches and says reject or accept or drop, that is really the decision that is then done. And if you try to override that further down, it doesn't work. And yeah, because of that, you should really plan out your IP tables before you run all these things, because it's not so nice to squeeze in new rules between existing rules. I think I would do it this way. I would probably write a script that generates all these calls and maybe just uses something like bash variables for the different VLANs, for example, so that you can change the way the VLANs work by just changing the variables, and then you don't have to change all the rules when you change, for example, the range for a certain VLAN, right? And you might even then do something like have additional variables like workstations, which you then set to VLAN 4, for example. And then you can make your rules really just for workstations, and then you don't have to care about hey, what is the IP range of the workstations, what VLAN is that, what is the IP range of the VLAN. Just I think this is really the most elegant way you can do it. Write a script, and then just if you ever want to change something, then you just rerun your script, maybe have a table flush at the front of the script, and yeah, then you can change your tables as you need them, and it's not such a pain to work with. Okay, that was all I wanted to show you today. If you liked this video, like it, share it, subscribe, and see you next time.